Later on, and you'll see, especially when you get to calculus 3, you're going to be seeing this. And this is our 10.3, and it's all about something called parametric equations. So we've already seen this in some way when we looked at our graph of a circle. This is, used when we introduced a unit circle. Because in that, remember, we had over here, we had a little coordinate point here. Over here is my angle theta. And that coordinate point was my cosine theta, sine theta. Or we said x is equal to the cosine of theta, and y is equal to the sine of theta. Well, this is what a parametric equation does. It defines points on any sort of relation. So this is what we call parametric equation of a circle. The parameter here is theta. The parameter is the angle theta. And if I want to define it, I can define it as a series of points. So my series of points are x as a function of theta, y as a function of theta, or cosine of theta for x and sine of theta for y. And if I define it this way, and I give some range for theta, so let's 0 less than or equal to theta less than or equal to, or less than 2 pi, but equal to, but it just doesn't make it as unique. So I can let theta range from 0 to 2 pi. That will chase out that circle. And what it is, we don't write it explicitly. Like if I wanted to create this, the equation for this, okay, the equation for this would be x squared plus y squared is equal to 1. I don't have to put that in there. I just have to put this parametric representation, and I could draw the same thing. I could do this, or I could also do the polar form, r is equal to 1. All three of those would give me the same graph. But this is what we call the parametric representation. And let me show you on Desmos. You can also do this on your TI calculators by doing the parametric representation. But I'm going to use Desmos because I can do all three at once. That's a little bit easier because I can put them all three on the same graph simultaneously. I'll get rid of that, this, and that. And what we know is put for x squared plus y squared equal to 1. There's our circle. In polar form, that's equivalent to r is equal to 1. I get the same graph as well there. Oop. Now I can also do this, so parentheses, and then do cosine theta. Oop. That's supposed to be a parenthesis here. Only comes in pairs, so let's try that again. Let me delete it, parentheses, there we go. Cosine theta, comma, make sure it's a comma, sine theta. It should have, what is that here? Must have something, cosine theta. Let's see, maybe I have something there. It only has the one variable. Let's see, maybe I messed something up. Cosine. Oh, okay, maybe it's just looking at too many variables over here. What if I get rid of some of these things? Don't know what to do with this. It should be easily constructible. I know I did this in the past. Well, if I, instead of theta, if I use t, I know it will work there. Let me try t. Call theta t. Yeah, it doesn't like the theta used here, so let's just call it t. And there we'll graph it. And then t is going to go from 0 up to, let's go to 2 pi. And there it is. So it doesn't like the theta value, but you can call it the parameter t. Theta or t is just the same thing, but it gives me the same exact graph in either way. All of these are 3 different ways of drawing the same exact equation now. And if you look at your calculators, I'll just show you again, if you turn this on and look at your mode, you do have parametric here. So if you go down a couple, I'm going to change this back to radians. And I can do it parametrically. I can click on that. And then if I go to my y, I'm given x and y of t. So over here, this would be cosine t, sine t, and the window t goes to 0 to 2 pi, so that should be fine. So I can graph it. I'll leave it there. It's going to be a squash circle. It looks like, but there it is. I could, if I get the aspect ratio correct, I can make it look more circular in nature. But you can do it on your calculator. That's all I wanted to point out. Except that I can't do everything on the same graph. That's what I like about this. I can do my Cartesian, my polar, and my parametric representation all on the same graph. Not quite possible with our calculators. They're going to be phasing out over the years. We're going to have more capabilities of using these graphing, software things in class. But this is an example of a parametric equation. Now, the benefits of this is several things. It can allow me to, it's not unique. For example, I would get the same graph if I did this. So parametric equations, just like polar forms are not unique, parametric equations are not unique. Forms are not unique. Meaning, I could have, cosine t, comma, sine t, or I could do this, cosine of t squared, sine t squared. Now, I would get the same graph. However, this one would go around more rapidly. Both of them would give me a circle. And you can start when t is equal to 0 and go to t is equal to 2 pi. So t is equal to 2 pi would put me, going around in this direction. Okay? I could also do this, but this will go around faster. Let's let t be time, and I'll show you what I mean by that. We'll go back to our Desmos picture over here. Let's clear this one out, and this is one over here. That's my standard one. Now what if I say this? Cosine of t squared, comma, sine t squared. Now, notice this is just going up to 1. This goes up to 6.28. Let me just put that out there. 6.28. So at least you can see it in numbers, 6.28. And that is the radian measure of 2 pi. Now, if I go up to, say, 3, or say 2, see, I'm almost there. Let's go to 2.5. It's actually a little bit less than that, so 2.4, 4, 5, 4, 8, 4, 9. Roughly, yeah, 495. Yeah, so it's very close to that. So if t was time, this took me 6 seconds to go around for the first one. This one took me roughly 2.5 seconds to go around, so going around faster. Now I could also go around in the other direction. I could also do this. Cosine of the negative of t, comma, sine of the negative of t. Now, in this way, I'm going in this direction, clockwise versus counterclockwise, if t is positive. Now, this will also go to, if I go all the way around in, 6.28 or 2 pi units. But notice I'm going in the other direction. I'm going clockwise versus this other one over here takes me around in a counterclockwise fashion. I'll start here and I go counterclockwise, just so you can kind of see what's happening. So what it permits me to do over here, this representation permits me to kind of give speed and direction to curves, which is kind of a unique and fascinating thing. So a parametric representation in general looks like this. Here it is. I have my x as a function of t, where t is the parameter, and y as a function of t. Again, it's not unique. But it allows me to draw a curve just like I can do in the rectangular or polar coordinates, but it allows me to make it go through that curve in a certain direction and at a certain speed, which can be very important if you're going to model things in the engineering or the physics world. And that's why it becomes very important there. And we trace around things called arc lengths and stuff like that. You'll see that later on. But this is my parametric representation of a curve or relation in the plane. This is a parametric representation of a curve or some sort of a relation in the xy plane. And the benefit of this allows me to set how fast I go around and which direction. So you can set how fast you go around the curve and in which direction. So for you guys, it's going to be relatively simple. You just have to be able to take a curve given parametrically and sketch it. You can throw that into your calculator or throw that into Desmos. I just want you to just have recognized this and be familiar with it. So it's not that hard. All you're going to be asked to do is sketch parametric curves and find its direction it's going. And just by changing t, as you let t, you can see its direction. Very simply. And just get a feel for it. So it's not too complicated. What we do here is simple to get you prepared. At least you've seen it once before you suddenly, it crops up again when you see it in calculus and you're learning everything at once. And at least, oh, okay, I know what it is parametrically. I can write it like this, and I change t, and it kind of goes around that curve. It changes my x and y, which changes my location in the xy plane. And you can trace out really elaborate-looking graphs if you wanted to. You can trace all sorts of things, and they can go in all sorts of directions that you want, doing it parametrically. That it's harder to do both in the polar and just about impossible to do in the rectangular. It gives you more power to represent more elaborate things in the world around us. Some things are not as tame as we present them. Okay, so that's essentially what you're going to do, is just find the start point. We can find the start point and the end point is here, and just plug that in and find the direction of a curve defined parametrically. And just do it on the board over here. You have a curve that some particle is moving in. You can specify it parametrically, and you can actually specify how fast it's moving by using that parameter t. So that t can make it, kind of go slow and then suddenly speed up. And it kind of gives you the ability to represent more complicated phenomena in the world. And that's the benefit of adding these extra concepts and ideas. It allows you to do more with it, to model the world more precisely. These are powerful tools that you will see in later mathematics courses. You won't really get a sense for what they can do right now, but later on you'll see it again and say, okay, I remember a little bit about that, so that helps me get one leg up as we move forward. The various relations parametrically, but what are their equivalents if you're looking at it in the Cartesian? So for example, now we're going to look at, the Cartesian equivalent, or the rectangular equivalent, to parametric curves. So for example, take a simple one over here. So I have x is defined as the parameter t, and y is the parameter t squared. So what is the single Cartesian equivalent to that? Well, this is relatively easy because everywhere I have a t, I can replace it in x. So I can use that over here. Y is equal to, well, t is x, so it's equal to x squared. So this is the equivalent representation of the parabola, written in parametric form as well as Cartesian form. So some are simple like that. Some might be a little more complicated. Let's take a look at this. Say, for example, I have x is equal to 2 times the cosine of t, and y is equal to 3 times the sine of t. Well, how do I in some way represent that without any t's, just x's and y's? Well, here's a little trick over here. I'm going to divide both sides of this by 2 and that by 3. So that's equivalent to x over 2 is the cosine of t. Y over 3 is the sine of t. This is what you try and do when you have sines and cosine. Let's square that first one and square that one, okay? So I get my x over 2 quantity squared is equal to cosine squared t. Similarly over here I have y over 3 quantity squared is equal to the sine squared of t. What I can do is, let's just, two equations, I can add them together and I still get equal things. So on the left hand side, this gives me, let's square it out, x squared over 4 plus y squared over 9 is equal to cosine squared t plus sine squared t. Our objective is to eliminate t. But what is cosine squared t plus the sine squared t? 1. T vanishes. So I have x squared over 4 plus y squared over 9 is equal to 1. We're going to find in chapter 12, this is something called the equation for an ellipse. So that's what we'll see. But anytime you have cosine and sines, you'd like to try and use the Pythagorean identity to eliminate them. Now some can be slightly more, elaborate as well too. Let's take a look at another one over here. I'll give you one last example. So say x is equal to 2t plus 1 and y is equal to, say, t squared minus 1. Can I combine them in some way to eliminate t? Now, what is the approach? Well, if I can, take one of these and solve for t and replace it in the other one. That's always one of the objectives. So I can take this equation here and solve for t. So I can do that. That's x minus 1 over 2 is equal to t. I subtract 1, divide by 2. Then what can I do? Well, I can take that expression for t and substitute it in over there to eliminate the t. So that gives me y is equal to, I'm replacing t with x minus 1 over 2, and I am squaring that and subtracting 1. And you can multiply that out and see what you get. So you can kind of see the approach. You have to eliminate the variable. So you can work with those two equations together to eliminate that variable or not. Now I could multiply this out, but it's not necessary. You can see it's going to be another parabola, if you will. This is a parabola, as you'll see, that's kind of going upwards, and it's shifted from the origin now. Okay, so that's taking a parametric equation and finding its Cartesian equivalent. Very simple. It takes a little bit of work, a little bit of practice doing the manipulation. But do this now, because later on in the math and the science courses, it's going to come at you fiercely. There's a lot of things that you have to kind of get up to speed if you're going to go in a technical discipline.